Hi everyone, welcome back to the channel. In the last section, or in the last video, I talked about how we had two different topics that were related to each other, something called linear approximations and the other one called differentials. And so this is a video about differentials. So in this video, we're going to focus on talking about the quantity that we've seen a lot, which is dy over dx. Okay, I know that another way to write this is y prime, and hopefully you remember kind of where this comes from. Dy over dx is talking about delta y and delta x, and another way you know that is to talk about that as a slope. And basically this quantity here talks about dy is actually representing the change in y, that's why we use that delta, and then dx is representing the change in x. So I want to kind of focus on this quantity in this section, where we can look at specifically the change in y and the change in x independently or separately. So what we're actually going to do is we're going to find dy dx, actually just like we did back in the past when we talked about implicit differentiation. It's actually going to be a lot like that, so really not much different. But then once we know what dy dx looks like, we're actually going to take that ratio of those lengths, or the ratio of those changes of dy and dx, and we're actually going to look at those separately or independently. So we're going to split up dy dx. Now, dy dx looks like a fraction, and even though it's talking about just a ratio of the changes there, it is a fraction. We can undo division with multiplication just like we always have been able to. And so basically what we're going to do is we're going to have problems where when we solve for dy dx and get dy dx all by itself, we're going to get dy dx equals, I don't know, something over there. And the goal is we're going to get dy all by itself. So it's actually perfectly legal and fine for us to say let's multiply both sides of the equation by dx and move dx to the other side. I know dy dx, we've been thinking about that as like one quantity that goes together. That's like a slope. But it is okay to multiply by dx over here and get dy equals something times dx. And really what this is doing here, we're going to be given some values at the beginning. We're going to have probably a specific type of function, and we're going to talk about a specific x value. And we're actually going to be given, in a lot of these problems, a specific value for dx. So we'll be given a specific value that says how much is x changing by. And usually that's going to be a small change. Remember in the last video when we talked about linear approximations, we talked about how if you're talking about a really big change in x, if the 2 points that you have are really far apart from each other, then you don't really, your estimate is going to be off by a lot. You're not really going to be finding something that's really valuable or really close to what we want. So for us, this specific value of dx is typically going to be a small value. You're going to see stuff like dx equals 0.1 or 0.01 or 0.2 or 0.25 or 0.25 or something like that, where it's very small. And so typically dy is also going to be fairly small, because what we want to know about is kind of a small window around the point where we're looking at a value of x and y. Okay, so again, not a lot new, just one or two extra steps added to stuff we've already done in the past. Let's go ahead and look at an example to kind of start out for us. So we're going to have something like this: y equals x squared minus 4x. And instead of saying find dy dx, which have been the directions really for a long time now, find the derivative basically, I'm going to modify just a little bit. Instead of saying find dy dx, now I'm going to say something like find dy. So you're going to move that dx over to the other side when you're given specific values of the other stuff. So I'm going to tell you that in this problem, x equals 3 and dx equals, I told you it was going to be a small value, so you should expect something that's not going to be incredibly big. In this problem, let's go ahead and use 0.5 as our dx. Okay, so let's go ahead and take a look. Again, what we would do in previous problems with implicit differentiation is we would say take the derivative of both sides. On the left side, you get something like dy over dx, and on the right side, you take the derivative with respect to x. You get something like 2x minus 4. But then we're not just finding dy dx. Remember, our new step now is to get dy all by itself. So go ahead and multiply both sides by dx. Now, I would just, one little caution, I hope that I don't even need to say this, but I'll say it anyways. Make sure that your function over on the right side, you put that in parentheses, because when you multiply both sides by dx, dx is going to actually have to multiply by everything on the right side. So 2x minus 4 all times dx over there. Okay, and now go ahead and plug in what you know, and hopefully the only thing left that you're finding is the value that we're trying to find. So we know x is 3 and dx is 0.5. We should be finding dy. Okay, so dy here looks like 2 times 3 minus 4 times 0.5. Okay, what? That's 6 minus 4 is 2. 2 times 0.5. That means we should be finding dy to be 1. Okay, 2 times 0.5. And so I realize that 1 is not quite as small, it's not a decimal, but that's okay, it's still not massive. We said that as dx is going to be pretty small, and then that's going to kind of force dy to be fairly small as well. This says that as x changes by a half a unit, y changes by a whole unit. Okay, so again, we could think about the graph that we drew in the last video that says, let's say you have a function here. What about, let's see, what was our x value here? It was 3, right? So at 1, 2, 3, if your x value changes from 3 to 3.5, there's our delta x change from 3 to 3.5. Here's your point when x is 3. Here's your point when x is 3.5. How much is your y value changing by when x changes by 0.5? So here's delta x is 0.5, and delta y is 1. By the way, this isn't a great picture because it doesn't actually represent the function that we had. The function that we had was supposed to be quadratic. I just kind of drew a generic function here, but really it should be it should have been the function that we started with. But you get the idea that as x changes by a little bit, y is supposed to also change by a little bit there as well. Okay, so yeah, let's go ahead and take a look at another example here. Kind of last one. So y equals the square root. Actually, I tell you what, let's change it just a little bit. Let's go with this one up here. Let's go with y equals e to the x over 10. Let's throw in an exponential. Okay, so same thing. We're going to find dy, and this time I'm going to tell you that x equals 0 and dx equals 0.1. Okay, at this point I would encourage you to pause the video. Go ahead and see if you can do this on your own first and then come back to it. Okay, did you pause? Great. Let's go ahead and take the derivative of both sides here with respect to x. So we're finding dy dx on the left side. And then on the right side, when you take the derivative with respect to x, it should look like e to the x over 10. But then there's a chain rule here. E is its own derivative, so that's good. But then there's a chain rule. You got to multiply by the derivative of what's inside, which is 1/10. Okay. And now you can go ahead and remember, our goal is not just to get dy dx, but to split those up and to get dy all by itself. So dy equals e to the x over 10 times 1 over 10 times dx. Go ahead and plug in your information that you're given at the beginning, and if you do that, you should get something like dy equals, let's see, e to the 0, that's just 1, and then times 1/10, and then, by the way, dx as 0.1, that's actually another 1/10, and so, let's see, dy here is actually 1 over 100, or you could write it as 0.01. Okay. Again, you shouldn't be surprised to see a really small value there for dy, and this basically says that as x changes by a little bit, 0.1, y changes by even a little bit more. In fact, this should probably give you an idea of what the function kind of looks like at x equals 0. Okay, because at x equals 0, you can think about what happens is that as x changes by a little bit, y changes by even a smaller amount. Like x changes by 0.1, y changes by 0.01. So you should expect this to be a fairly flat curve, or at least at x equals 0. We don't know what happens further away from x equals 0, but close to x equals 0, you should expect this to be fairly flat because as x changes by a value, y changes by an even smaller value. It doesn't go up quite as quick as it moves over to the right. Okay? All right, I hope you've enjoyed these examples and this video talking about differentials.